We thank you for the results of these lessons, and we pray that we may go through this lesson smoothly and the rest of the lessons as well. Pray that you may give us the gift of understanding, and pray that we may internalize the questions properly, and that we may be able to remember all that we learn and be able to apply it in our daily, everyday life. Yeah, we pray that you may be with us, and we thank you for the provision that you have made. We bless you. In the mighty name of Jesus Christ, I prayed. Amen.
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 I said
Yeah, amen. So over to you, Mr. Senjobe. I see you around. If you're ready.
Good afternoon. Sorry, I moved a little bit away from here, but good afternoon, people. Good afternoon.
Good afternoon, teacher.
Good afternoon, Mr. Senjobe.
You're not helping. You say help.
Okay. Okay. We had started on work, power, and energy, and I think we had gone through some small exercises as far as work is concerned. And I think we want to progress. There's a document I'm looking for, I want us to share. This document. Okay. So I think we are done up to number 6. We are looking at work done by friction force. Okay. Can anyone tell us what friction is? Do you see the document, girls?
Yes, teacher.
Yes, teacher.
So I hope we see the document. Teacher. Let me see. Anybody, let us remind ourselves about friction force. Okay. So what is friction force?
We have people had put up the hands. Okay, there's Atkwasa Kelly.
Friction force is a force that opposes motion.
The force that opposes motion. Thank you so much, Lindy.
Teacher, I had the same answer.
The same answer. Mr. Sanjo, are you satisfied with the answer?
No.
May we have another participant? Yes, Ayoki.
Friction is the force that opposes relative motion between two surfaces that are intact.
That are in the last statement, that are in
intact.
Intact.
Okay. Who can correct that word?
Can someone correct?
In contact.
In contact. Thank you so much.
Two surfaces that are in contact. And she has used the word relative motion. So under normal circumstances, friction only comes into play only when one surface tries to move over the other. That is when friction starts coming into action. Otherwise, if a body is simply resting on a surface, there is no friction. But the moment it starts to try to move, then friction comes in and tries to oppose that motion. Is that okay?
Yes.
So that is friction. It is always going to oppose the motion that is between any two surfaces that are in contact. So we usually have a very simple illustration. In your notes there, you see a body. These bodies were not labeled, but there is a surface, there is a body, a box, there is a force acting on it. That force is trying to drag the body through a distance x. So it is shifting it from one position to a new position until the distance moved is distance x. Now, when you apply a force, there is a force that comes into play between the two surfaces. And that force is trying to oppose the motion between the two surfaces in contact. I want you to look at my video and concentrate on what I'm going to draw on the board. I think it will give out a better display of what we're trying to say. Can you see this part of the board?
Yes.
Mr. Sir, you are saying something?
Okay, we can see. It's only that the spaces. It's okay, we can see.
Okay, there is a surface. It is resting on a surface. I'll label that as my surface. I'll apply a force. And that force is labeled as F. And the moment this body starts moving, something happens. Between the two surfaces, there is another force that comes into play. Do you see the color I'm trying to use? I'm trying to look for other color, but I cannot see that color. There is another force here which comes into play. Do you see that force? Do you see that color?
Yes.
So this is what we call, this force here is what we refer to as friction. Now, this direction here is the direction of the what?
The load.
No. Look at the arrows. What am I written here?
Motion.
So the body is moving in that direction. Is that okay?
Yes.
But where is friction acting?
The opposite direction.
The opposite direction. So that is what we refer to as opposition. This friction opposes that motion. Is that okay?
Yes.
Now this friction is also labeled by the letter F. Now this body is moving from this point until it reaches that position. So it moves through a distance which has been labeled as X. So the new position of this body is maybe there. That's what you have in your notes. Is that okay? So what is the work done against friction? This is what we are going to discover. That the work done against friction, can you see here?
No.
No, we can't.
My laptop is a little bit constrained because it is charging. Can you see it here now?
Yes.
Yes.
Work done against friction, work done against
Friction.
friction is going to be given by the product of the friction times the distance moved. Is that okay? Is that okay, girls?
Yes.
How do we find the work done against friction? Give me the equation.
Friction times
Distance.
What?
Move. Distance.
The
Move.
distance moved by the object. Is that okay? By object over the body. Distance moved by the body. Okay? So that is how we find friction. So in your working, you have the letter F standing for friction, and you have the letter X standing for distance moved. That is how we measure the friction. And what is the unit for that work? The work must always be in joules. Is that okay, girls?
Yes.
Okay. So let us look at the friction done, the work done against friction. I'm going to request somebody to read for us that subtitle. I think I've explained it. Mr. Moses Sali.
Okay, we have Wiyenza Charity.
Work done by frictional force. When a force is applied on a body resting on a surface, frictional force is developed between the surfaces in contact and tries to oppose the motion of the body. Hence, work has to be done to overcome friction. A force F is applied to a body so that the body moves with a uniform speed through a distance x in the direction of the force. Since the body moves with uniform speed, the frictional force is also F. Therefore, work done by the applied force is equal to F times x. Work done against friction is equal to F times x. In this case, the useful work done is 0, and the work done by the applied force is dissipated as heat and sound energy.
Okay, so that work done is always given out. That is what we mean by the word dissipated. It is transformed into heat and sound energy. That's why we always say that friction results into unnecessary heat and sometimes sound. That heat is not usually unnecessary because it can be used to also create fires. I hope you understand that.
Yes.
Is that okay? So
Yes,
the work done is going to result into heat, it is going to result into sound, it is going to result into wear and tear. You remember friction causes wear and tear. Is that okay?
yes, teacher.
No,
Hey, you don't know that friction causes wear
I
and
don't
tear?
understand how the useful work is.
The useful work. Okay, anybody who has an idea
The
what we
useful
refer to
work is
as,
the useful work.
okay. Work can be broken down into 2 or 3 components. Let me put it this way. There is what we call the work input. That is the work, you know, most of these things are going to be related to the later topic which you are going to be discussing. It is going to be machines. But not everything that you put into an engine is useful. For example, when you get into a car, what do you want to do?
You want to go
Right.
somewhere.
You want to go somewhere. Is that okay? So the purpose is to carry you somewhere, isn't it?
Yes.
Now, when you start a car, in most cases, let us consider the purpose is to move you somewhere. Was the purpose to bring the car also?
No.
No. No.
The car is a means of bringing you, isn't it?
Yes.
Yes.
You cannot move without it. So the useful work is to carry you from one place to another. However, amidst that movement, you have to tag something along, and that is the car. So the car which you have brought, you also do work in moving the car from one place to another. That movement of the car, in most cases, I may categorize it as useful, as useless work, though it is part of the system.
Yes, teacher.
So the major purpose is to move a person from one point to another, but in doing so, the person may need a means of transport. So you may ride, you may go on a boda, you may go on anything. So you end up bringing or dragging certain things with you. But these things, they are not going to do anything there. They are just part, because if they are not there, you can't move. If they are there, they assist you in movement. So that's how machines work. Machines will do the input, then part of it is useful, the rest is useless. And we are going to realize that friction is part of the useless works under normal circumstances. I have laid the background on that, and I'm going to leave it at that. So work can be broken down into work input, work output, and work wastages or useless energy. Is that okay? That's how we shall get that equation for energy later as we go through this topic. Okay, so thank you so much for that reader. I want us to recognize that I want us to look at that particular example. I think it will give us an idea. We brought in these inclined planes, people. I don't know whether they were not too early here. What do you suggest? Is Mr. Sally still present?
No.
Yes, Mr. Sanjove.
We brought in these inclined planes at this level. Are they and they going to make
I wanted the inclined plane to clearly bring out the useful work done, and then the useless work. Just that it is not a complicated number.
Okay. Okay, girls, let us use this process to try to understand what we mean by work input, work output, and so on. So can we request a lady to read for us that example?
Okay, someone raise up your hand. Someone who hasn't said anything. Noella Asimwe.
The box of mass 30 kg is pushed with a force of 130 grams up an inclined track of length of 14 m onto a platform at a height of 5 m from the ground. Take G is equals to 10 kg. Calculate A, the work done. Calculate the work done by the force of 130. The work done if the box was lifted vertically upwards. And A and B. C.
Okay.
The box and the track.
Okay, girls. Can we look at and try to understand that question? Are we together?
Yes, teacher.
Okay.
Yes, teacher.
Let us look at that box. What is the purpose of that question? What if you look, a box of mass 300 kilograms is pushed with a force of 130 up an inclined track of length that to a platform of height. So can somebody tell me what the purpose of that system? What is its major purpose? What is it supposed to achieve?
Lift the load upward.
What is it supposed to achieve? These are common scenarios that will come. People who have shops and they are loading trailers, they know this. People who have ever raised what? Yeah?
To simplify work.
Yes, we are simplifying work. That is okay. But what is our purpose in simplifying this work? What is our purpose? What is the aim?
To ease movement.
Get work done. To oppose
But the challenge is, girls, you are not thinking. You are only giving me, yes, I want work to be done. That is it. But what kind of work? What is my aim? That's what I'm asking you. Look at the box and what
lift the load upwards.
Lift the load up.
Lift the load to a height of 5
So be
meters.
specific. Through what distance?
A distance of
14 meters.
14 meters.
A distance of 40 meters.
14.
14 meters.
14 meters. That is the purpose of lifting it from 14 to 14 meters. Hey, who can give me the right purpose? Yes, you are lifting it, but through what distance?
5 height of
5.0 meters.
Exactly. The purpose of that inclined plane is to lift a box from a lower level to a higher level. And the higher level is 5 meters above the original. Is that okay?
Yes. Yes.
So your purpose is to raise the box's height through 5 meters. So originally it is at a lower level, and then you are going to lift it to a height of 5 meters. So the purpose is to lift the box through 5 meters. That is the useful work. So how can we get the useful? Then there is also, in order to achieve that, we apply a force. What force is applied?
Motion.
What force is applied? Read the question.
Friction.
A box of mass 30 kilograms is pushed with a force of
130 newtons up and
Guys, you are
inclined.
murmuring. It is pushed by a force of 130 newtons. But if we look at that force, the way it has been applied, through what distance does it move?
14 meters.
The weight it is going to move along a distance of 14 meters. And that is going to be the work done by that force is going to be the force times the distance it moves. Is that okay? And that work is going to be referred to as the work input.
Yes,
that work is going to be called the work what?
input.
The work input. So how do we get the work input? You know the answer. The answer is there. Work is obtained as a product of force and distance.
The distance moved.
So what is our work input?
1,820 joules.
That is our work input. Okay. Now, the next question is asking us, work done in lifting the box vertically upwards. Is that okay? Can we find that work? The work done in lifting the box vertically upwards. Here, we are considering the vertical displacement. So, how do we find that? I want you to explain that. Work is always calculated as force times distance. So how do we get this force now?
The force, there is gravitational force, so you multiply the mass of the box by the gravitational force to get the full force.
So this is going to be weight of box times I get these things. Some things I want, I don't know that I can get them. It is weight of box times, what is the times thing? I don't think I can get what I want. Let me leave it. Okay, what I wanted to put there was weight of box C times the vertical height. Vertical height. It is trying to explain our notes. So we get the weight of the box This will be given by an equal sign here. This is equal to the weight of the box times the vertical height. So our weight is given by mg times the vertical height. Our height should be, actually, I want to change that letter to h. And then we get that. That is how we get that work. And this work is now called the useful work.
Yeah.
That is the useful work. That is the intent of the inclined plane, or it is called the work output. So for those who are supplementing that is our work output. Now, the second question is asking us, the third question, the two are different. Some work is used to overcome friction. So this is how we go to the energy conservation. Is that okay? Energy conservation equation. Do you remember the energy conservation?
Yes, teacher.
You told me energy conservation.
No.
What is it?
Conserving energy.
How you conserve the energy that you don't have to use a lot of effort?
The law of energy conservation says that work can neither be
These are what can
Or
neither
lost.
be
Destroyed, but rather transferred to other forms like heat.
Energy can neither be created nor destroyed, but only changes from one form to another, as the sum total always remains the same.
Okay, that is very good. So in this case, if you are to get this equation and understand it properly, I'll include the following: that work input is going to be equal to the work output plus work done against friction. Is that okay, girls?
Yes, teacher.
So our total work will always be equal to the work done by the force plus the work done against the friction. So in other words, we are trying to say that the work input is always equal to the work output plus work done against the friction. So I think now we can get the work done against the friction as the subject, isn't it?
Yes, teacher.
And it will be our total work, which we got in part A, subtract away our useful work, the work we got in part B, and that difference is 320 joules. That is the work done against the friction. Is that making sense?
Yes, teacher.
So therefore, for us to get this work done against the friction, we get it as a product of the friction force times the distance moved. And remember that that distance is going to be moved by the distance of contact. It is going to be distance of that plane, that long plane there. So the distance is given as 14 meters, but the friction is not known. So the question is looking for friction force, and I hope we can get the work done against friction is 320. The friction force we don't know. The distance is the length of the plane, which is 14 meters, and that enables us to get the friction. So what is our friction?
22.9 Newton.
22.9 Newton.
Is it clear?
Yes, teacher.
Okay.
No. Somebody is saying no. So where did we lose you?
On the total work on C. I got lost.
Yes, I've just told you that if we want to understand this, I have labeled part A. What did I label part A to be?
Work
Work
input.
input.
the work input. Then we got the purpose of the aim of that system was to lift up the box through a vertical height of 5 meters. So the weight of the box represents the force, and the vertical height is represented by the distance h, and from the diagram, h is given as 5 meters. I think you've seen that. So we have got the useful work done, or what we call the work output.
Yeah.
So we have said that from the principle of conservation of energy, the work input is always equal to the work output plus the work done against friction. Is that okay?
Yes.
So you make the work done by friction the subject, which will always be the difference between the input subtract away the output.
Yeah, I've understood. Thank you.
And therefore we can now calculate our friction. So that is our friction. Is that okay, everyone?
Yes, so teacher, the total work.
Yes, please.
What work is this?
So teacher, the total work done is the work done by the force of 130 newtons.
Yes, that is the work done I'll actually call it the work done by the effort.
So it's the total work done.
Yes, that gives us the total work done.
Okay.
Then the work done by the load is what we call the work output. The work done on the books, because our books represent the load. So that is our work output. The purpose was to get the load from through a vertical height of 5 meters. We are using an inclined plane. And I told you the inclined plane is a machine that eases work. Is that okay?
No.
What is not okay?
Teacher, okay, I'm just asking a question. If you're finding work output, can you say effort times distance moved by the effort?
No, work output is about the load.
No, work input.
Input, yes. Work input is the effort times the distance moved by the effort. It is effort times the distance moved by the effort.
Okay, thank you.
While work output is the load times the distance moved by the load.
Thank you.
Okay. So the difference is usually the work wasted, and this work is wasted in terms of friction, sound, and heat. Is that all the friction in actual sense in this case? Is that okay?
Yes, teacher.
Is that okay, girls?
Yes, teacher.
Okay. So that example is actually trying to give you the principle of conservation of energy. That's what it is all trying to do. Okay, let us see what we have here. There are how do we handle this exercise, Mr. Sally?
No letters. No letters.
Okay, girls, can we have that heading of power?
Yes, teacher.
Yes, please. Can somebody guide us through that? It gives us an understanding of what power is all about.
Consider an object of mass being pulled along an inclined
let us be disciplined.
plane.
Let us leave the reading to one person.
Thank you. Consider an object of mass being pulled along an inclined plane of length L to a platform at height h by 2 students, one at a time. One student takes t seconds while the other student takes 0.5 t seconds. Both students do the same amount of work. However, the second student does the work faster than the first student. Therefore, power measures how quickly work is done.
Okay, so we can be given the same amount of assignment or work, but some people do the same assignment faster than the others. So we are talking about the rate of working. How do we transform energy from one form to another as quickly as possible? And in most cases, when we talk about the rate of working, we are talking about what we refer to as power. Is that clear?
Yes.
So even when we are given assignments, there are some people who do their assignments faster than the others, and therefore their rate of working is quicker. They do their work quickly and do other things. So under normal circumstances, you find that the higher your rate of working is, the more productive you are likely to be. So power is a measure. It is a measure that is used for most machines, and they'll give you the rate of working. So depending, if I'm given a machine and it has a higher rate of working compared to the other, I'll go for that machine because it will do my work faster compared to the other. Am I making sense now?
Yes.
Yeah?
Yeah.
Okay, suppose I have people and a certain person does a job or a task faster than the other. For you, what would you choose? You choose the slow one or the faster one? Or it depends?
The faster one.
Or it depends?
Faster one.
Okay, but anyway, it depends on the task. Is that okay?
Yes.
Let me give you an idea. Why I'm saying it is depending on the task. Suppose you had a bulb and it was labeled 100 watts, and then another one was labeled 5 watts.
100
What would you prefer?
watts.
100 watts, that's what you prefer. 100 watts. And you have another bulb, it is labeled 5 watts.
100
What
watts.
would you prefer?
5.
Mubadechi, you girls, what is wrong with you? Go and look at power savers.
Yes.
Power savers must have low rates of consumption of energy. The more energy you consume, the cost increases. So that's why I told you it depends. Is that okay? Is it okay? Because remember that what you put in is what you get out. So there is a cost attached at the end of the day. Anyway, what I'm trying to say is the power gives us the rate at which work is accomplished. Is that okay? That is our definition for power. So let us look at the definition for power. Somebody read.
Definition.
Power is
The rate of
work.
doing work.
I asked the person who was assisting me to select the people. I don't know that Mr. Sal is back or not.
I have a question.
Yes,
you have a
Mr. Sanjove. Mr. Sanjove, I'm here.
And you keep getting out in and out, so Munanga, you lose it. Okay,
I have a question.
who is helping me? Somebody has a question.
Yes, I have a question.
Yes, please.
I was asking this concept of power that you were just explaining. Is it the same concept that is applied when making the vehicles?
That is applied in vehicles.
Yes.
Yes, it is.
Okay.
Though the meaning may be slightly, the meaning may be
How about
may be
electronic
different.
vehicles?
You are shouting. You are not listening to me. Are you ready to listen now?
We're listening. I don't know who was interrupting.
Okay. Power, I've told you it is the rate at which work is done. And I've told you that yes, the meaning, because most machines are going to be rated, they'll give you the rate at which it accomplishes. And these rates will carry different meanings. From not wise to have bulbs with high power ratings because they'll consume a lot of energy per second. Is that okay? But for vehicles, machines like that, when they give you their power, you are going to discover that they can carry bigger loads. The more powerful your engine, the bigger the load it can carry. So you cannot have a small vehicle having a higher power rating compared to a trailer, for example, because a trailer is made for big loads. So its power ratings are very big.
Okay.
Am I making sense? So
Yes.
tractors and for vehicles, these ratings are labeled in horsepowers. I don't know that you have heard about that horsepower.
Yes.
Yes.
What does it mean?
About what they mean by horsepower. Okay. So what we have said is the rate of doing work. Is that okay, girls?
Yes.
So we get power,
Yes.
we calculate power as the work done divided by the time taken. I hope that is clear from your notes. And the SI unit for power is a what? What's the SI unit for? It is out. Now, can you pronounce it? Can you pronounce it properly so that you differentiate it from this normal word?
What?
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 Okay.
What?
Okay. So if you say what, and the teacher asks you Ogambachi, you can say, I was talking about the unit of power. Is that okay?
What?
Yeah, I know now we are talking about the unit of power. So a watt is the equivalent to 1 joule per second. And what is its definition? I want one reader.
A watt is the rate of doing work at 1 joule per second.
At 1 joule per second. That is our rate of doing work. That's our definition for a watt. Okay. So please keep that definition because I told you whenever you see something highlighted or whatever, that implies that is something important to keep because the question may arise out of that. Okay. So our my reader continue.
In the sense of power being defined as rate to transfer of energy, we can also mathematically express power as power is equal to change in energy over time.
Over time. But I want to add this simple word. Time taken. Is that okay?
Over time taken.
The time taken for that change to occur. So that is our measure for power. Okay. Then we have the different conversions. I'm not going to waste time with those conversions. I'll say you be there for yourself. Okay. Okay, you be there for yourself. You can do the conversions of words and so on. That one we shall look at it as we look at the questions. Okay, first example.
Calculate the power of a water pump which can fill a water tank 10 meter height with 3,000 kilograms of water in 20 seconds. Solution.
I had gone out of the class because somebody else is making a lot of noise in the background. I don't know who. There's a lot of background noise. I don't know whether that can be removed so that we listen to one person. Okay, read the question again.
Example 1. Calculate the power of a water pump which can fill a water tank 10 meters height with 3,000 kilograms of water in 20 seconds in brackets. Assume grams is equal to 10 meters per second.
Okay. So I'm going to be specific. Let me see. Somebody has gone out of this class. I don't know who. I'm going to pick on someone called, where is Kendra? Kendra Katsime Chirabo. Kendra Katsime Chirabo. Chirabo. Kendra is not here. Okay, I'm going to look for someone. Ukunda Agatha. Ukunda Agatha. Okay, Ukunda Agatha is not here. Let me pick another one. Natabona Lindsay. Natabona Lindsay.
Yes, teacher.
Okay, Natabona Lindsay. Natabona to correction. Are you okay? Are you with us?
Yes.
Okay. So in our solution, what are the major components that we pick out? They are there in the solution. So just read them and you tell us. I want to see whether you understand what they are talking about.
Solution. M equals 3,000 kilograms. H 10 meters. G equals 10 meters.
What does HM stand for? What does M stand for?
I'm not sure.
Read the question. Do we allow this? I did the isolation intentionally so that others can pick from her and we know what a lesson looks like. So her example, if she presents a bad example, I'll know that we have bad examples in the background. So please read, what does M stand for? Read the question because everything is picked from there.
Okay. The power of a water pump, which can fill a tank of 10 meters height with 3,000 kilograms of water in 20 seconds. Which I don't.
Okay. You don't know, really, you don't know what is measured in kilograms.
Mass. Mass.
I hope you are now back. You understand that the unit has been given, the unit must give you the quantity it is measuring. So mass of what? Let us be specific about this example. That's how mostly you lose out. So mass of what?
Mass of water.
That is our mass of water. And we are lifting this mass of water through what distance?
A height of 10 meters.
Please, whoever is interrupting is simply being indisciplined. Yes, you know, but keep quiet. I want my student to answer so that she gets something from this lesson. So what does H stand for?
H stands for the height.
The height through which we are going to lift that mass of water. Then our G is the gravitational acceleration. What is the question?
Calculate the power of a water pump which can fill
So we are looking for power. We are looking for power. Now look previously at the top of your equation. What is power? At the top of this equation, what is power is given by?
Power is the rate.
Can you allow power is given by, that is our equation.
Power is work done over time.
Work done over time. And what is work?
Force Distance.
Very good. So in this case, we don't have force, but we have mass. How are we going to find our force? Please read, everything is there. That work is a product of force and distance. But the force in this case represents what? What does it represent?
The mass, mg.
Is that mass? Mg, is it mass?
Wait.
Weight.
The force is actually the weight of the water. That's why we have it expressed as mass times gravitational acceleration. That is our weight of the water times the distance that we are going to lift this water through. So our mass is given as, can you now substitute in the formula? Mass is given by
3,000
times the acceleration, which is
10
times the height, which is
10.
10. So what is your work done?
It's 300,000 joules.
Very good. That's how we find the work done. Now the question is asking us for the power. So how do we go now and find the power?
Power is work done over time.
So we get our work, which is
300,000 over 20.
And what is our time?
20.
Our time is 20 what? What is our time? Read the question. The unit for time.
Seconds.
So when you are calculating power, girls, listen very carefully. The time must first be converted to seconds. It is very, very important. That is when you get your power measured in what unit?
Joules per second.
What is the unit for power? It is a watt. That is exactly. Hey, when I ask for what is power, you say what? Unit for power. You understand? What is the unit for power? It is the opening statement. What is the unit for power? It is what? Does that make sense now?
Yes.
Hey, unit for power, they ask you, what is the unit for power? You say what? You are done. Whether you made it or not, it is okay. Is that okay?
Yes.
So the unit is a watt. That is it. Have we understood, girls, how to answer that question?
Yes, teacher.
Yes.
I have specifically highlighted one person to answer the question because we are 140 something and very many people have started getting out of the room. So you can see how many people are understanding. Maybe because some of them have prior knowledge, but because of that, please, I don't know what is happening at home, but I know if I'm at your age and I'm studying at home, it is not easy. It is really a challenge, and I really give up those who are inconsistent because there are so many disturbances.
Yes, teacher.
Okay, so please concentrate and understand. Is that okay?
Yes.
Teacher.
So there is another method, but that method, it's simply the other one. It is just a quicker method. Work done divided by time is force times distance divided by the time, and we get that equation. So that is how we find that work, okay?
Yes.
It is one. I want to stop here. The rest of the examples, I want you to look through them. Is that okay?
Thank you, teacher.
Yes, thank you.
Thank you, teacher. Bye.
Thank you,
teacher, for the lesson. Happy birthday, Uganda.
Thank you, teacher. Bye.
Bye.
Thank you, teacher.
Okay.
Happy early independence.
What's your problem?
Happy Independence. We just saying bye-bye. Happy Independence. Happy Independence.
Happy
Is today independent?
I'm not allowed to leave.
Early.